This lecture series will introduce you to a few basics of convection that develops on the mesoscale in the tropics. Clouds organized at the mesoscale, which is approximately 100 kilometers in dimension horizontally, are responsible for the majority of observed precipitation in the tropics. In the first module, we'll start off with a discussion of convective and stratiform precipitation. As discussed in the previous lecture series, cumuliform convection occurs with a continuum of depths, up to clouds that extend from the boundary layer to the tropopause. A population of shallow convection overcomes inhibition in dry air to eventually grow into deep convection, and as divergence aloft from deep convection causes moistening of the near cloud environment, anvil clouds that are laterally expansive compared to the parent convective elements from which they develop begin to form. Systems of numerous individual convective elements that are connected to a stratiform region are known as a mesoscale convective system, or MCS. MCSs are typically 100 kilometers or greater along one horizontal dimension. They transport large amounts of water to the upper troposphere and through its extensive anvil clouds distribute it far from where convection initially developed. As a result, MCSs are a significant contributor to upper tropospheric water vapor, promoting the development of tropical cirrus clouds. MCSs occur throughout the tropics, subtropics, and mid-latitudes. They frequently occur over both continents and oceans. The current figure highlights where MCSs occur in the tropics. The top three panels indicate the locations of MCSs, defined by size, in boreal winter, and the bottom three panels indicate the sizes are the same during boreal summer. MCSs are common over the Indo-Pacific warm pool year-round. During boreal winter, they frequently occur over southern Africa and Central South America. Large MCSs are common also over the maritime continent during boreal winter. During boreal summer, the bottom three panels, MCSs are more common in the northern hemisphere. Many more occur in the ITCZ, in the Atlantic, East Pacific, and northwestern South America than during winter. Small MCSs are more common in southern North America as well, and associated with the North American, put in quotes, monsoon. MCSs are frequently observed in Southeast Asia and West Africa during boreal summer as well, largely associated with summer monsoons in those locations. MCSs with a variety of structures exist, and the shape of an MCS is largely dependent on the background environmental structure, including the wind shear. A canonical MCS is often represented as a system with a leading convective line and trailing stratiform region, which we will discuss more soon. The schematic shown shows such a system. A convective region is horizontally narrow, but contains intense updrafts that can overshoot the tropopause in this region here. The heaviest precipitation in an MCS occurs near these updrafts. Moisture advected laterally out of the convective regions into the purple circles supports the development of anvil clouds both ahead, which is to the left of in this figure, and behind the convective cell. The blue region indicates where relatively light stratiform precipitation occurs. Above the 0 degree sea level in stratiform, essentially above 5 kilometers in the tropics, deposition occurs and releases latent heat. This drives upward motion. Melting occurs as ice hydrometeors fall through to 0 degree sea level, which causes a radar bright band to appear due to the difference in dielectric constants between liquid water and ice. Evaporation of liquid water occurs below the 0 degree sea level, which consumes energy from the atmosphere and causes cooling of the ambient air. The precipitating regions advect moist air at upper levels into the surrounding environment, form these non-precipitating anvil clouds denoted here by purple circles. A leading anvil, which is in front of the convection, is usually small, but the trailing anvil can extend rearward of convection for hundreds of kilometers and persist for hours to days after precipitation dissipates. Anvil clouds enhance upper-level shortwave heating, experience long-wave heating near their bases, and all the clouds experience long-wave cooling right at their tops. The net rate of heating that occurs in anvils reinforces the latent heat release at upper levels in stratiform regions. The diabatic heating helps to reinforce upper level upward motion on the mesoscale. Examples of anvil clouds seen in West African MCSs are shown here. In the top left is reflectivity from a vertically pointing cloud radar as an MCS passes over it, with time on the x-axis. The MCS is moving from right to left, if you consider this to be distance on the x-axis, so the leading anvil is present to the left of the gray box. This leading anvil is close to the deep convection, which is denoted by the echo-free region beneath the gray box that indicates strong attenuation of the radar beam, and is higher in altitude than the trailing anvil at the rear of the system. At the bottom panels, derived long wave and short wave heating are shown, and the total heating, the sum of the two bottom panels, is shown at top right. Three idealized profiles of latent heating in convective and stratiform precipitation are shown in the top panel. One is for shallow convection, which in this case refers to moderately deep convection like that in the congestus mode, except that this convection is cumulonimbus. It has a peak of vertical motion and heating around 2 to 3 kilometers and no heating above about 6 kilometers. The deep convective heating profile extends through the depth of the tropopause with a positive sign and has a peak near 6 kilometers. These peaks in heating denote the levels at which the most condensation occurs in cloud. The stratiform heating profile has a peak positive value in the upper troposphere and a peak negative value in the lower troposphere, with a change in sign around the 0 degree sea level. The heating and cooling are dominated by deposition and evaporation respectively. The exact depths and shapes of real heating profiles are much more complicated, but these simple functions capture heating to first order in the three major types of precipitating tropical convection. They can be combined to produce linear combinations of the idealized profiles that characterize the mean net heating profile within an MCS that depends on the relative precipitation rates in deep convection, stratiform, and shallow convection. The deep convective profile looks like the first baroclinic mode in the troposphere, while the stratiform and shallow convective heating profiles look like opposite sign second baroclinic modes in the troposphere. We'll describe the baroclinic modes a little more shortly. These types of profiles can be confirmed using a numerical model, as shown in this figure, which further divides convection into a few additional categories and identifies the convection based on the simulated low-level reflectivity field. Mean vertical velocity and latent heating on the right are shown respectively on the left and right panels for different categories of rainfall. In the model, deep convection tends to still have heating throughout most of the troposphere, as seen by the dark blue-purple line, although cooling below 800 millibars may be associated with heavy rain in convective downdrafts. Stratiform precipitation, the red line, shows heating aloft and cooling with a peak below the 0 sea level, but latent heating in the model shows near zero heating below 800 millibars, which may or may not be realistic. The shallow convective heating profiles are denoted by the light blue colors and include cooling above the convection, particularly in this weak convective fringe, that is likely attributed to long-wave cooling. In summary, the modeled profiles resemble the idealized profiles to first order, but show some interesting additional complexities. A little while ago, we referred to convective heating profiles as resembling baroclinic modes of the troposphere. This encourages a short discussion of what barotropic and baroclinic modes are, although we will discuss them in more detail mathematically when we discuss equatorial waves later in the quarter. The modes refer to gravity wave modes of motion that occur in an idealized multilayer fluid. A barotropic mode, which is known as the external mode, describes a vertically averaged motion within a fluid. In the barotropic mode, density is only controlled by pressure. You can visualize this by a wave in an in-layered shallow fluid, approximating the troposphere as the shallow fluid from the tropopause down to the surface, in which the crest and troughs are aligned with depth in the fluid. In baroclinic modes, density of the fluid is controlled not only by pressure, but also by temperature, humidity, or salinity. You can imagine the first baroclinic mode as a wave in which the crests are spread out throughout the depth of the troposphere and the troughs are close together, or vice versa. In the troposphere, the crests spread out are denoted by hypothetical contours of theta E, representing deep warming through the troposphere, which resembles a latent heat release in deep convection. Cooling throughout the troposphere is the negative first baroclinic mode, which is somewhat similar to mean radiative heating throughout the atmosphere, although the vertical structure of radiative heating in clear air has maxima in the upper and lower troposphere. Here we visually compare the first baroclinic mode to the second. The second baroclinic mode might consist of heating aloft that spreads out crests through the top of the fluid, but compresses them in lower layers of the same column, or vice versa. The positive second baroclinic mode has heating aloft and cooling in the lower troposphere. This resembles the combined heating profiles caused by diabatic heating in stratiform and non-precipitating anvils. The opposite case with heating in the lower troposphere resembles shallow convective heating topped by radiative cooling aloft. Convective and stratiform regions can be challenging to detect in satellite imagery. The example shown here is a visible satellite image of an MCS located near Panama. The deepest convection is not immediately obvious, although some deep convection might be suspected north of Panama. The infrared brightness temperatures at the same time highlight the coldest cloud tops in the red colors. These are likely close to the convective precipitation regions because the coldest cloud tops occur as a result of deep convection reaching high altitude and promoting stratiform cloud aloft. Further from the convective clouds, these green colors for example, the tops of clouds are typically lower as hydrometeors subside. Combined with clouds being optically thinner further from the source of the convection, the higher brightness temperatures indicate where stratiform precipitation or non-precipitating anvil is located. Precipitation is difficult to detect using visible and infrared radiances alone. However, radar can detect echoes of various strength that occur beneath the cloud tops seen by a satellite. The current figure shows radar echoes from the tropical whirlpool in a variety of different scenarios. The top left shows isolated convection that is characterized by several small, scattered, isolated cumulonimbus. The top right shows a more convectively active state where convective echoes, such as these that I'm pointing out right now, those with the high reflectivity approximately greater than 40 dBz, so the reds and pinks here, are larger. And the surrounding weak echo regions, in the greens, where hydrometeors from convective echo were transported laterally. The bottom left illustrates an example of an eastward moving leading squall line of intense convection followed by a trailing stratiform region of weaker echo. And the bottom right depicts a large stratiform region with embedded convective elements located within it somewhat randomly. These variety of structures are often difficult to identify easily by simply consulting radar imagery and require some sort of active sensing instrument, or at least passive microwave. As you may have gathered from previous slides, a cloud population tends to evolve from one that consists predominantly of shallow convection first. Deep convection then develops, followed by lateral expansion of these deep convective elements. Eventually, the formation of broad stratiform regions signifies the mature stage of the convective life cycle. This progression can be seen in the figure shown here, which shows radar-derived time series of rainfall associated with each type of convection as a function of time relative to the peak rainfall time of several convective events, where my mouse is here. And the colors correspond with the different types of convection. The evolution resembles the progression seen in the drawing at the beginning of this module, from shallow to deep, and then deep and wide convection. This evolution from convection to stratiform occurs on many different timescales also. Previously, you just saw how convection evolves on an approximately 2-day long period for a convective event that was regional in spatial scale. The current figure shows the evolution of convection in stratiform in a larger scale phenomenon, the Madden-Julian oscillation, of a 30-day long period. If you just focus on the black lines in each panel, the left is for stratiform and the right is for convective, you'll see that the convective rain rate maximizes on average at the time that the peak precipitation occurs within a 30-day event, while stratiform precipitation amplitude is largest a few days after. The general lag of stratiform behind convective rainfall makes sense because deep convection is a prerequisite for the formation of stratiform.